Hey, welcome back. Today I'm going to show you an example problem demonstrating strategies we've been using and need to use for AP Physics C mechanics, specifically in our rotation unit, and we're building on some of the ideas that we've been using throughout the entire year. I'm going to show you how to do this. This problem comes from the College Board. It's a modified version of a problem from the College Board. Although crucially, you don't have to be an AP Physics C mechanics student to be able to handle this. There's no calculus here, and it is rigorous, but it's something like a good high school physics class could cover, or maybe an honors physics class could cover, and students should be able to understand what's going on here. Crucially, I'm going to show you the strategies that you need to know to be able to solve problems like this. All right, let's go ahead and get to it. So first of all, the problem says there is a chain that is attached to the end of a rod. The other end of the rod rests against a wall. So it rests against a wall. That's important. This is effectively not attached. So it's not attached right here, but there are forces that are holding it in place. So we'll be talking about those forces and thinking through how to think through this problem here. The other end of the chain is attached to a point above the contact point with the wall. They're talking about this right here. The rod does not slip against the wall. The question is, what is the tension in the chain in terms of m, the mass, theta, and constants? In case you can't read that, I'm going to try to rewrite that as theta and constants. Okay, so let's go ahead and talk through how to do this. First things first, we're going to start with a free body diagram of what's going on here. So we've got some forces. If you want to pause for a second and do this as best you can on your own, go for it. Now's a good time to pause if you choose. Okay, and so let's move forward. Let's think about our forces here. We've got some forces. One force is going to be called the force due to friction. I'll just call it force due to friction here. You could call it static friction force. We've also got another force operating right here. That's our normal force. There are a couple other forces. We definitely have the force due to gravity. That's the force due to gravity for the rod. That's going to be applied at the center mass for the rod. We're going to assume the rod is a uniform rod, so that's going to be applied at the center of this length right here. There's another force operating here, and that is tension, and we need to talk and think about this theta angle as well. Alright, so those are our forces. Let's start thinking about our strategies. The first strategy we're going to work through is what I call the sum of the forces strategy. So the sum of the forces in the x, you literally add up the forces in the x. Let's define some directions here. We're going to say to the right and up are positive, down and left are negative. There's also going to be a torque component, so I might as well define that as well. Any torque that's going to cause a counterclockwise rotation is going to be considered to be positive. Any torque that causes a clockwise rotation is going to be considered to be negative. Alright, and so those are our terms and our directions that we need to deal with. Let's go back to our strategy. The first line for the sum of the forces strategy is just to simply sum up the forces in the x-axis. So what do we have? Well, we've got the normal force, and we've got a plus minus tx. So you literally are adding up the forces in the x-axis, the sum of the forces. And there are just these two forces here. And then the sum of the forces in that axis are also equal to mass times acceleration in that axis. So now at this point, it's appropriate to ask ourselves, is that acceleration something or nothing? So what do you think? Is the acceleration of the x of the rod something or nothing? Well, the answer is it's nothing. So that means it's 0, and so we can set these equal to each other. So we can therefore say Fn minus tension of the x is equal to 0. So therefore Fn is equal to tension of the x. In terms of magnitude, that's a true statement. I'm going to box it. We're going to come back to that later. Then we're going to work with the y-axis. Sum of the forces in the y. And let's think about our individual forces in the y. We've got Ff, we've got tension in the y, we've got a negative force due to gravity for the rod, and that's it. Then we have the sum of the forces in the y is equal to mass times acceleration of the y. Is our acceleration of the y something or nothing here? What do you think? Well, it's nothing. That means that is 0. That whole term is 0. We can set these equal to each other. Ff plus tension of the y minus force due to gravity of the rod is equal to 0. Now, Oftentimes there are a couple different things we can solve for. In the y-axis, a lot of times we have the normal force. We don't have that here. Our normal force is in the x-axis this time. So we actually don't know really if we need to solve for our force due to friction or our tension of the y. We can do it both ways, actually. We can isolate for both. So let's do that for both, just because at first glance we're not quite sure what we're going to need to work for or with or solve for. Minus tension of the y. So that's one isolation right there. If I isolate for the force due to friction, we can also isolate for tension of the y, and we can say, well, that would be Fg minus the force due to friction. Then the next strategy is going to be to draw on the x and the y-axis and work with friction. Friction is special in that regard, and that's why it's a generalized strategy. It's a good strategy to work with, is to use the friction equation. So I'm going to use a generalized friction equation here. We can use the equal sign when we assume maximum static friction, for instance. And so I can say that is true right here if we're assuming maximum static friction. Now, typically what I would do is I would have students just sub in what we know. We do know something about the force due to friction right here. I can bring this around and plug that in here, and we do know something about the normal force over here. Can draw this with dotted lines going in here and see what would happen. So we could say Fg minus tension of the y is equal to mu times Fn, we know, is just Tx. And now it's really important to recognize, oh, we've got tension of the y and tension of the x. We need to treat them as if they are variants of one variable as opposed to two variables. So let me explain what I mean. First of all, I'm going to quickly draw this vector off to the side, call it tension. This is theta over here. We'll say this is tension of the x, tension of the y. What we're going to do is say tension of the y is equal to tension times the sine of theta, and we'll say tension of the x is equal to tension times the cosine of theta. I am skipping a couple algebraic steps, but I think at this point you probably are okay with this. So now what we're going to do is take this equation, and again, instead of writing like tension of the y and tension of the x and treating them as if they are two different variables, we're going to treat them as if they are one variable. Let's simplify Fg as well. Just immediately call this mg, and we'll say minus, and then this tension of the y we said was tension sine theta, and we have is equal to mu times tension of the x is tension cosine theta. Alright, and simplifying, we can just get our tensions on the same side of the equation, so we would have mg is equal to mu tension cosine of theta plus tension sine of theta. And what we can do with that is we can draw out, let me show you, we can draw out the tension, and that would give us mu cosine of theta plus sine of theta. And we can isolate, and I am out of room, so I'm going to move this down and just say we've got tension is equal to mg, and that is mu cosine theta plus sine of theta. Okay, so this is a pretty standard, straightforward problem so far in terms of solving for this kind of thing. I think at this point, hopefully you should be able to do this. But notice that there's no mu. There is no mu allowed. There's no mu allowed. I guess you could consider mu a constant here, yeah, but let's just say, let's do this a different way as well, using a different set of strategies that are actually really important as well to understand how to approach these kinds of problems. So we've done forces, we've worked with forces, but we can also do this in terms of torque as well. So I'm going to maybe work up here for a bit, and I will draw this with a different color. So we're going to do a rotational analog to what I've been talking about so far with our strategies. I've called this sum of the forces strategy, so we did that in the x and the y, and then combine them with friction. Here what we're going to do is what I call the sum of the torque strategy, and it's just the rotational analog of this. And this is where we get a really, really crucial strategy. And the strategy is set your axis of rotation well. So for objects in rotational equilibrium, it's really crucial to understand you can set your axis, and I'm just gonna simplify this as A of our axis of rotation right here. It's really, you can set it anywhere for an object that's in rotational equilibrium. That's not rotating, that's not moving. You can actually set it anywhere. That's what we're going to do here. And if you do that, you actually eliminate one of the torques. And I'm going to prove that to you in a moment. So let me show you how to think through this. So we're going to say we've got some torque. So we've got some torque from the friction, right? And we've got some torque from the tension. And we've got a negative torque from the force due to gravity. And then the second line for the sum of the torques strategy is, instead of m times a, that's Newton's second law in a linear sense, net force is equal to m times a. We're going to do this in a rotational sense, and we could say that the net torque is equal to I times alpha, moment of inertia times angular acceleration here, or rotational inertia times angular acceleration. Then what we can do is set these equal to each other, and if we do that, we end up with this. Oh, let's pause for a second. I times alpha, let's think about what is alpha for this stationary thin rod. What do you think? Well, alpha is going to be 0, and if that's the case, that whole term goes away. So we can just say that whole term is equal to 0, right? Now, what else do we know about torque? Well, the equation for torque is going to be this, R crossed by F. And so what that means is we want the component of the force that's perpendicular to the first vector, and that R value is the distance between the axis of rotation and where the force is applied. Well, in the first example, this torque from friction, that distance is 0. So let me explain what I mean. We can just say, well, that would be 0 times the force due to friction, right? Plus, and then let's think about where that torque from tension is applied. Well, that would be at length L. So length L times the tension in the y-axis. So that's true for the second term. And then third term, let's think about where the force is applied. Where is that force applied in terms of L? Well, that's going to be applied at L over 2. That's where the force is applied. And this we're going to say is the force due to gravity, which is just mg. So all of that is equal to 0. In terms of saving space, I'm going to write this up here. I can say L times Ty minus L over 2 times mg is equal to 0. So therefore, L times Ty is equal to L over 2 times mg. And what do we notice in terms of simplification here? What do you think we can do? Well, we can cancel out the L, right, for both of these. And then we can just say tension of the y is equal to mg over 2. Okay, so we've got more info here. We've got tension of the y. Now notice we did come up with something previously where we talked about tension of the y. We said at the very bottom of the page, I'm going to put an arrow pointing to it right now. We also know tension of the y is tension sine theta, right? So let's write that in. So we could say tension sine theta is equal to mg over 2. And so just to clarify and to solve the problem effectively, you could say tension is equal to mg over 2 sine theta. And so that's how you would go about doing this kind of strategy right here. That's going to be your answer right here in terms of tension with these variables without using mu. And using these strategies here, you should be able to be comfortable with these strategies that I've gone over here for using the sum of the torque strategy and also figuring out where to put an axis of rotation for an object that's in rotational equilibrium. You can set that axis of rotation anywhere. That's in the white letters right there. And the crucial thing is you want to set it at a point so that the torque is equal to 0 for that. In other words, if our axis is right there and our force due to friction is right there, then it's fair to say this axis of rotation causes this torque to be equal to 0, which simplifies the problem for us. So that's how to think through problems like this. I do want to say I've gone over an entire year of physics as well as most of the concepts for an AP Physics C mechanics class. So if you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.